have this done speaking, I don't know, I guess when I'm done speaking, I can see you guys, but there is no reason for me to do that. Is the audio okay?
Yeah, it sounds great.
Fine.
Okay, good. All right, great. So basically, I don't know, should we start with questions? Because I already have everything pretty much on my introduction and on the talking points. Or I can just go with, and basically, I don't know how exactly to start it. There is this philosophical point where you defined what general intelligence is. Okay, and people either agree on it or they disagree on it. It's pretty hard to convince someone who disagrees. So my definition is somewhat extreme. It doesn't include any anthropomorphic stuff. It doesn't include motivation other than curiosity. It doesn't include judgment other than just patterns, because to me, judgment is just another pattern to learn. It doesn't include much of anything. This is just a general cognitive ability, which I pretty much reduce to pattern discovery as opposed to pattern recognition, where you are given a pattern and you're supposed to find it in the input. Pattern discovery is when you actually compose patterns out of discrete inputs. Okay, so I don't know if we should go over it. Again, the pattern in my terms is pretty much the same as a cluster, except that cluster is defined through match. That is, you first have to do a comparison among inputs. Okay, if you find a match, the set of matches will be a pattern. Okay, so you have a bunch of inputs, the vector on the input, and you form a pattern out of it, or a cluster. And this process is hierarchical, never stops. It's basically an indefinite process of exploration. You go through the input, you have a feedback that redirects you to maybe some other areas of input, or inputs at different resolution, different modalities, different whatever. And the system is supposed to basically just increase its predictive power by exploring the environment. I don't know if we should go over this point again, or you just move on to the technical part.
I think I missed the definition. What is a must?
The definition is intelligence is a general learning ability, which means pattern discovery. Okay, the difference between learning and just basically a recording is that learning is selective, and we have to define the criteria for selection in general terms, not as in, okay, go get some food or go, find a mate or some other shit. In general terms, you look for patterns and you filter out noise. Okay, and once you have those patterns, you figure out what to do with it. It's like it's the unsupervised part of learning where motivation doesn't enter. Any motivation other than just basically increasing predictive power of the system, which comes from patterns. Okay, pattern is what you predict by. If you have a pattern, you can project it, continue it, and that gives you a prediction.
It makes sense. In a way, it's almost easier not having a presentation to look at, because there's less to be distracted with. You just, listening, you know.
Right,
So
and to me, it's actually easier to do it in text, but
yeah,
whatever. I mean, I understand that there is a motivating part in having a voice and all that, but the texting gives you time to actually compose a good reply or to make sense of the previous replies or whatever. And in real time, you don't have that time.
yeah. So I mean, just in terms of an overview, so I know you're working on some, or you've had some people working on this software. On what does it do? I mean, in terms of so, could you give us like an example problem that it would solve?
There is only one problem that I care about. That is pattern discovery. That's all. And as far as the people, I did have a few people coming in and out. I do have one long timer who has been on the project for about 2.5 years. He's helping a lot. There were a couple other people that contributed, not a whole lot, but I did have some contributions, mostly on a programming level. Just you know, figuring out the code and making it work. And so the idea is the system starts totally naive. It doesn't know anything. Okay, all it knows is a stream of input, and those inputs must be raw because they can't be language, because language is a pre-processed language input. Language is something that comes out of some other people, okay, who already looked at the environment and encoded it in symbols. In the nature, in the actual environment out there are no symbols. It's all analog. Okay, so if you want to build a standalone system, it cannot start with symbols because symbols are encoded, and the more encoded, the more difficult it is to decode it, to actually see the patterns that the symbols stand for, because symbol is just a label. Okay, it doesn't mean anything by itself. It just stands for something else. And that something else is the actual pattern that represents that raw input, which originally is analog. Okay, so the first step you do with that analog input, okay, which there is really no choice to it because that's what all things in the universe are. Unless you process it, it's just basically analog input, audio, video, tactile, whatever, that comes in, and then you discretize it, split it into limits of resolution, which is an equivalent of pixels in the video. You digitize it to compress it because that's what basically it is. You can put it in the unary code, but that will take too much space, so you just digitize it. And actually, that compression is the first step of that whole process pattern information, because those patterns are also defined by additive compression. Okay, when you compare inputs, you find out what's the common part of those, and that common part can be compressed. I call it a match. Anyway, so this is the idea. There is only one place to start. Okay, it's a dense array of integer inputs. Okay, those pixels. There is no other place to start because everything else would start from some pre-processed input that comes from some other cognitive system, and you don't know how it was processed. Okay, that's what language is. Okay, you know what the words mean, but the E system that just kind of started up, it doesn't know what it means. The only reason you know what it means, what those symbols mean, is because you as a child, from the moment you're born, spend a year or two observing things before you even begin to speak. Okay, that process of observing is when you actually discover those patterns, and then once you have those patterns, you can slap labels on them. Okay, those labels are words. Unless you have those patterns, you have nothing to slap the labels on. So those labels mean nothing.
Your system eventually creates some kind of labels though, correct?
It has references. It doesn't need labels in literal terms because it is standalone. You only need labels to communicate with some of the system, which basically a label is a shortcut. Okay, instead of communicating with images, you can have again, this is a hierarchical process, the process of discovering more and more abstract patterns. And you can slap labels on those more abstract patterns. And then when you communicate to another system that also has those patterns, okay, you need a shortcut between those patterns in your mind and the patterns in someone else's mind. And so those labels are basically a shortcut between those two kind of patterns. But it's really trivial thing because the way you learn it is pretty much the same as supervised learning works. Okay, it's labeled input. Okay, which means that you feed an input, you have labels on it, and that's how the system works. Okay, that's how it works in a child. Okay, the mother says that this is a doggy. Okay, you see a dog, you have a pattern of a dog, and you slap a word dog on that pattern. Unless you actually see the dog, it means the word dog means nothing to you. Does that make sense?
Well, yeah, I mean, that's basically the way humans are. We're excuse me, communicating in language and symbols, but the internal pattern is hidden. I mean, I can't see your neural arrangement of dogs.
Well, it is hidden in your mind. That's why, but if you do have this labeled input, you don't actually need to see it because you have an activation pattern of sorts that is triggered by the dog, and that pattern can be triggered by the label. That pattern comes with the label because you see that label on a whole bunch of those patterns that similar patterns that come in. Okay, so you associate the pattern with a label, and next time you see a label, that label triggers the association with the pattern. So you don't actually have to make it transparent, you just have to do this training process. But again, you only need it for communication. Okay, standalone system doesn't need it. It can make sense out of universe without using symbols because it's standalone. And that's the starting point. You don't, the reason to design an algorithm, to this panel discovery algorithm that will actually build a predictive model of your mind, you don't need those labels at all. And once you have that model, it's very easy to associate the patterns in it with the labeled input. So right now, I don't care about symbols at all. They really make no difference in the design of the system.
So Boris, I'm curious, what is the goal of this? Are you creating
the goal is to explore environment and increase predictive power of the system. I know you guys talk about motivation, you talk about 4 Fs, you know, for 4 Fs. It's fight, flee, feed, and fuck.
Yeah.
I could care less about that.
So how is yours different than other like clustering algorithms?
Well, everything is different because it starts bottom up. Normally, clustering algorithms are designed for statistics and they're designed for sparse input. That is input that is already being pre-processed by some. It's basically a symbolic input. It doesn't come. They don't actually use the same process for pre-processing and clustering. Okay, so the only reason you can get a sparse input is when you first sparsify the dense input. That is, initial input you get is the array of pixels is not sparse because you don't know what to skip. Essentially, you don't have any empty space because you don't know what the inputs are. You have to actually look at them before you can separate the pixels that have value and pixels that don't have value. All right, so basically, the initial step is when you have a dense array of input, you go through those inputs, you form patterns of them, and then you can, basically you have positive patterns that have above average value, and the negative is the space between patterns, and that's how you get sparse input. Now, if you look at algorithms like k-means or let's say k nearest neighbors, they all assume that the input is already sparse, that there is a space between elements. And that space doesn't exist in original input. It only appears once you filter out the relevant parts.
So you're talking about a kind of transformer.
Transform is a very general term. Anything can be called a transform. So yes, initially what you do, I don't know if you guys can see the first part of my introduction. I actually put a scheme on it. The first table.
No.
You mean yeah, I saw you had updated your documentation. I can post a link in a minute.
But it's basically it's the same link, and I already have it in the comment.
Oh yeah, I could share my screen real quick.
Thanks. Sorry, I've never really
the ones
used
with inputs comparison.
Yes, so basically you have this multi-level process where even digitization is interpreted. That table, do you see that table in the first page?
Yeah.
Of
We can
introduction?
see it.
Okay, great. All right, so in that page, even digitization is basically interpreted as comparison, which would be the first step on each level. Okay, each level of processing has this comparison clustering steps. And I didn't invent digitization. It's used everywhere where you use signal processing. Okay, but it fits this model because this is kind of like zeroth order of comparison where you have unary inputs. You end them. Okay, and that's how you get the higher digits. You convert the unary input into binary coded integers. So what it does is, again, AND is one of the forms of comparison that I defined as inverse arithmetic operation. Okay, it could be subtraction, it could be division, could be logarithmic extraction, but it actually on the opposite end, starting like before subtraction, it's AND. That Boolean logic is really zeroth order arithmetic. Okay, so when you get to two unary inputs, you compare them by AND. Okay, that AND operation basically checks if they both exist. All right. So, and in my terms, comparison is the process where you compute match and miss. So that end gives you a match. And there is no miss because those are unary inputs. They don't have parts. They either match or they miss. There is no partial miss. Anyway, so what I'm trying to get into is that even the most basic process that is used universally can be fit into interpreted as this process of comparison and clustering. Okay, comparison between unary inputs and clustering them into binary coded integers. And then, and in this case, you don't have external parameters. That is, those inputs are all in the same pixel. And the next step is what normally called age detection, which is actually a cross comparison between kernels. I don't know if you guys into this, but this is what it does. It computes gradient, and the way you can compute gradient is basically by subtracting diametrically opposed pixels in the kernel, like 3x3 kernel. And that subtraction is the second order of comparison. Okay, you compute the difference between them, and then you combine differences in gradient. So that is what basically a comparison between pixels. So that age detection, which is also used everywhere. It's a universal process. There is no signal processing without it, practically. Like no image processing. Every CNN or even transforms, they use this kind of cross comparison within a kernel, however that kernel is defined. They don't call it cross comparison though. And I think that's the problem. That's the reason for this conceptual confusion, where you don't see it as part of the same process that goes through multiple scales of this kind of generalization hierarchy or pattern discovery hierarchy. But this is what all those image processing algorithms do. They do age detection where you compute gradient, and that is what one of the second step of that cross comparison. All right, so again, it's all very basic stuff. And what I'm trying to say is the blank system must go through all those steps on its own. And once you have those steps in the chain, at least conceptually, you see how they correlate. And then from that correlation, you can discover what the next step is next level of processing is gonna be. Okay, so on that table, I'm showing the 4 steps, initial 4 steps of input processing. And basically here, the system is completely standalone. There is no pre-processing. Okay, you just have this environment, the analog input, and you incrementally cluster, discretize and cluster that analog input into more and more generalized patterns.
It seems like a real, I mean, what I got from reading your webpage and hearing you talk, it seems like the really important thing that you stressed is that you start with the like you're saying, the analog input. You don't start anywhere else. You start the same place that
yeah, you can't
start.
Because that's what universe is. Universe is analog.
Yeah, so I mean, you say, like you say, an analog input. I mean, could that? And when I think of an analog input, I think, from my electronics background, I think like some voltage, level. So the voltage between 0 and some value. But
yeah, basically, it's not completely. It's never completely analog. Analog assumes that there is an infinite resolution of sensor, and the sensor never has an infinite resolution, so it's really not analog. It's unary. That is, you basically You have the scale from 0 to whatever, and initial input is basically the number of ones. Okay, it's a technical distinction. You can call it analog, but strictly speaking, analog means complete exact correspondence between the input and the record, and you never have it.
You're
Okay,
talking about unary to get infinite precision.
right. Right. So basically, again, this is very different from AGIs you normally talk about. They like to talk on high level, which is symbolic processing. They talk about language. They talk about values. They talk about all those abstract things, but they don't exist until the system starts learning.
Just in practical terms, you could also input audio, correct?
Right. Right. It makes no
You
difference.
could-
Audio is just
yeah.
another modality.
Right.
And so basically the only two things that you have to predefine, you have to define a modality, which is a type of a sensor, and you have to define dimensionality. And this would be Cartesian dimensionality. You can do it in 1 dimension, you can do it in 2 dimensions, 3 dimensions, but generally speaking, the universe is 4-dimensional. So if you do it in 1 dimension, you're missing a whole lot. Now, I do start with 1 dimension only as a test case just to develop the code. It's not gonna, the actual patterns, 1-dimensional patterns, they're not gonna be terribly predictive because they kind of open-ended in vertical dimension and depth and so on. So they only predict in 1 dimension, and it's just not useful. Even audio is actually not 1-dimensional. We like to think about 1-dimensional because audio is usually used for speech processing, and speech only comes from 1 source, and it is sequential, so you can treat it as 1 dimension. But again, that's symbolic stuff. The actual audio out there in the universe is 4-dimensional, just like video. I mean, that is the physical universe that we live in. We don't have a choice over it. It has to be 4-dimensional. So the ideally, logarithm is gonna, it could theoretically start with 1, which is the base case, which is the algorithm only knows time. Okay, that 1 dimension. And then it figures out that time, that 1 dimension actually not enough. There is some kind of periodicity in the input that can be interpreted like if you scan lines, if you scan horizontal lines vertically, you find that those 1-dimensional patterns, they actually match over a certain period of time, and that period gives you a vertical dimension. And that's just an example. And it's like it is again very different from the way neural networks work because they don't have a separate positional parameter. They are fully connected at the bottom. Okay, they just have a bunch of inputs, and essentially, if you have the most basic type of unit, like a type of node in neural network, which is perceptron, the output has no information about position in the input. Like you have a bunch of inputs that converge in the output. They're basically summed into output. Okay, during that summation, position resolution is lost. It's gone. And that is generally not an idea technically because position matters. Because for predictive purposes, you have to know what and you have to know where. Okay, it doesn't really help you to know what happens if you don't know where it happens. All right, so I have this comparison with neural networks, artificial and biological, and generally they have to be very different, but they only different if you have nothing outside of it. From my point of view, INN and brain actually operate on very similar principles. I mean, similarity is a matter of degree, of course. If you have something very different from both, then they look similar. And if you don't have it, they look very different. So again, this process that I am designing, it is extremely different from the way neural networks works because it's not destructive by default. It doesn't merge inputs just for the hell of it and then see what happens. Okay, it has to compare the inputs first.
So Boris, when you
Yeah.
when you're training the system, can you actually?
Yeah, don't train it. Let me just explain the difference between learning the way I use it and training. Training is a vertical process. Okay, you have to do it through feedback from higher levels. The way neural networks work, they start from random inputs, random weights. Okay, and the reason they randomize it is because, again, there is a general assumption that those inputs, they mean nothing until you have this training process kicked in. And the training process is vertical. Even in Hebban learning, which is supposed to be a local rule where you don't go through multiple layers to get a feedback, you have a feedback right there within a node. From the output of the node, you have one node, one neuron that have a bunch of inputs and one output, and then what happens is you compare the input to the output, and if you have a match or coincidence, then the weight is increased. If you don't have that much, then the weight on the input is decreased. So that is the most basic kind of learning, and it's vertical. That is between input and output would be an input to the next layer. Now, in my process, I have lateral cross comparison between inputs. You don't have an output yet. The first thing you do, so this is the difference. The very first step that you do with the input, in neural network, you do weighted summation. In my case, you do cross comparison, which is a lateral process between the inputs, not between input and output. And so I don't have training other than through adjusting hyperparameters or what I call filters. Training is it's basically fitting. It's a very brute force method because you have immediate destruction of resolution. You sum the inputs. In my approach, you don't destroy the resolution until you have a chance to evaluate each input. And the way you evaluate it is through match to other inputs within comparison range, which is what age detection does. It's a cross comparison. And so there is no training here. Okay, the training is vertical learning and clustering is lateral learning, unless it's a centroid-based clustering. Okay, this is a connectivity-based clustering, which is between the input as opposed to between input and a centroid of a whole bunch of different inputs. Okay, so in neural networks, the output is basically centroid. It's normalized sum of inputs. Okay, so there are two different kinds of clustering in very basic terms, the connectivity-based and centroid-based. Connectivity-based does training, and the centroid-based does training, And that lateral connectivity clustering, it forms patterns right away before you have an output. And the output in this case is already patterns.
Boris, you usually have two inputs to your system.
What do you mean?
Like different modes, like vision and hearing, for example.
No,
Well-
it can work in one modality. There basically, a priori, there is no limit to how many modalities you can use.
It's like in
Okay.
traditional neural networks, you have a training value and a signal. Two
Yes,
inputs.
the training value is a feedback, and you can't have a feedback before the feed forward. In my case, I first define this feed forward process. Okay, so that's why the first step is lateral, because you don't have a feedback yet. The higher levels don't exist. In neural networks, you design a fixed depth of, let's say, n layers of neurons. In my case, you add those layers one by one sequentially. Okay, so again, it's really very different from the way neural networks work.
Basically, you start by going laterally.
Yes.
Just to, yeah.
Yes.
Yeah.
Initially, you only have inputs. You don't have feedback yet.
Well, what
It's just one input. There's not two inputs. It's not a.
Sorry?
You don't have two values that you input. You only have the input.
Well, the input is not one value. The input is discretized. It's a bunch of pixels. So when I talk about inputs,
Analog value.
well, yes, the first thing you do with that analog, with those analog values, is you discretize it into pixels and then you digitize pixels. So
Right.
there is no positional cross information yet, because those pixels are zero-dimensional. They basically stand alone, and it's not what normally would be called cross comparison. It's only a digitization process. Once that's done, the input is an array. Okay, and when talk about inputs, I'm not talking about the whole array. I'm talking about elements of that array. And cross comparison is basically a comparison of each input to all other inputs within a comparison range. If comparison range is initially 1, and let's say you have a dimensional array, then it's a cross comparison within 3 by 3 kernels. So the point I'm trying to get across here is that inputs here are not the whole, let's say, frame. Is the pixels of that frame. Does that make sense?
I think I basically understand it. What I was kind of driving at with my other question was, it seems like one result of your structure is that you can examine patterns somehow, right, after the fact. Like, I mean, a big complaint we all know about neural networks is that they're typically opaque. But it sounds like, I mean, it looks like you're almost putting together properties. You know, given some input, you extract patterns, you create, or you isolate what matches and what misses. But it seems like the result of that you could then examine somehow, like in a way that you might not be able to do with a neural network.
On this level, right after comparison, you can, because CNN, they basically do the same thing. They do cross comparison within kernels, except that cross comparison is it depends on the weights, and the weights are trained first. It really does pretty much the same thing, very similar thing to what happens in sub-L kernels. Okay, except that there is some kind of a different variations in the weights they put on the elements of those kernels. So on that level, it's not really that different. What is different is that I quantize the input in the next step. That is the two steps in knowledge level. There is a cross comparison step, and then there is a clustering step. And what clustering does is it groups a bunch of inputs into a cluster, which is more abstract, simplified, compressed representation of elements. Okay, and so basically when that happens, in neural networks, you don't have that. It's not, you don't have those discretized outputs. It's all distributed. It's not sparse. Okay, in the typical neural networks, you have a bunch of weights and inputs that have one-to-one correspondence on all levels. You don't actually, you kind of group those inputs through weights, okay, because some weights could be zero, okay, and so you have this effectively sparse output, but you don't actually have this sparsity in local representation. You don't actually have, how should I put it? Again, I guess the good way to put it is distributed versus localized representation. Distributed is when all memory is in connections. Localized is when each node has a local memory of whatever parameters, patterns that it receives from lower levels. Once it has this localized representation, local RAM, which is impossible in biological neurons, that's why they don't do it. They simply don't have a substrate to it, for it. Okay, they're really very primitive systems compared to digital microprocessors. Okay, so basically once you have this capacity to represent things locally, you don't have to go all the way across the networks to figure things out, because you already have stuff, you can process what you have locally. And this networking is generally extremely expensive, especially in biological networks. You have to actually grow those connections, you have to prune them. It's really, if you think about generic terms, it's ridiculous. So what happens here is once you assume that the node has the capacity to locally represent data and locally represent the program or whatever, you have the code that could be stored locally, it really simplifies a whole lot of things. Okay, the distributed representation is very, very expensive in just about everything. Or even if you do it through GPUs, you have to have this pipeline stream of inputs that where you have ridiculous amount of data coming in and out of the chip all the time. That's why they're so expensive energetically. All right, so once you have these representations, each node represents essentially a pattern that is encoded inputs. And then you can have pipelined hierarchy. That is, it's not a bunch of layers where the lower level representation basically stay on lower levels. And you can't really have continuous input stream. You have to have those training cycles, okay, where you go back to original inputs in the same network to adjust the weights. All right, if you have a pipeline, the input, the data comes in all the time. It replaces the old data on all levels. That all data is not necessarily destroyed by replacement. It just goes up and it is encapsulated in the higher level nodes. because they have RAM, random access memory. Okay, and so this process doesn't have to be destructive. It doesn't have to be this catastrophic forgetting thing that happens in neural networks. Okay, the reason it happens is because once you have a new input, it replaces everything and the old input doesn't exist anymore. If you have a pipeline, that doesn't happen. The old data is simply being pushed forward, and then it, on higher levels, it can be represented selectively. That is, if you have information-rich data, that is the data that fit patterns, it is represented in compressed form. And if you have a noise where you don't have patterns, then that's filtered out and you don't represent it. And so again, the reason why you can have that discretized versus distributed representation, when you can actually split data into patterns and represent in a more compressed fashion efficiently, is that we have modern computers which have memory, which don't have to rely on connections to represent every single bit of data. Just think about it. Bits are extremely cheap and connections are extremely expensive. And in biology, they are the same thing. You can't have bits without connections.
Well, an individual neuron is quite complex, though. It does have.
It is complex, but that complexity is in a number of connections.
No, it's connected by itself. Just one neuron is very complex.
Yes. But the neuron is, when you say neuron complex, you're talking about the dendritic tree of the neuron.
And the proteins and all its machinery.
Yes, it has a lot of machinery, but a lot of it is metabolic. A lot of it is just maintenance. A lot of it is
All I'm saying is,
repair processes.
like
And if you want to talk about information processing, there is some modulatory processes that do work through the soma, but they work in a very coarse fashion compared to actual inputs. There's a difference between modulation and the actual driving inputs. All right, so the driving inputs is where most information is, and those inputs are out there in the dendrites.
On the other end, for a machine, computer, the distributed process is can also be quick. It just has high latency in it.
It doesn't only have high latency, it also has, again, it's very expensive, both energetically and whatever, to pump the data through the interfaces between the memory and the processor.
But
that's one thing. And second, this is why in GPUs, they don't use sparse processing, because it really doesn't make any difference. Okay, you don't save much. And so they're basically stuck. They don't save much because they can't save much because of the whole networking model. Even though it's not a network, strictly speaking, you can process data sequentially, but the design is still like a network. Okay, and that's why you know how Numenta always talk about sparse representations, and they don't actually translate into efficient representations because they don't have those processors. And even if they could design the custom processor, it's not really gonna be helping much. Because they really,
if you can get a slice, however many dimensions you have,
yes, you can slice them all, but each slice is going to be dense.
Down to a latency, which doesn't take any more. If you have an infinite amount of time, it doesn't take a big time slice.
Right, you have those slices, but those slices are not sparse. They still represent all the weights and all the inputs.
But you can have a pattern to describe the slices.
Yes, but this is why those GPUs consume ridiculous amount of energy, because even if the inputs, the weights are zero, you still have to process them.
So you want a smart memory rather than a dumb memory.
Well, it's sparse because it is internal to the nodes. Okay, it can be sparse because basically you don't have to distribute the whole. You don't have to process the whole slice. Okay, you don't even need an input. Okay, the node can just sit on the process itself in internal memory for some time. It's more like an input through message passing as opposed to the whole dense input stream.
Boris, one question. The clustering, is that always happening on spatially adjacent nodes of information?
I'm sorry?
The clustering that you do, is that always happening with adjacent information? In your example, in your document, you have this one-dimensional string of data elements, and you combine adjacent elements there by clustering.
No, adjacent is just the first step. It's like I have in that table. This is the second level of processing, and then it is adjacency because that search goes with incremental. The cross comparison, it happens with incremental distance. Now, when you have inputs as, let's say, and that's how you form blobs. The blobs are contiguous. But once you have blobs, they have dimensionality and they can be compared over some distance. They don't, basically the distance between the comparants is increasing exponentially as you go up in the hierarchy. Because it depends on the predictive value of the input. Initially, all inputs have the same, assumed to have the same predictive value, but then you can separate strong patterns from weak patterns, and the strong patterns can cross-compare over great range, and the weak patterns, they basically disappear. They don't cross-compare at all. They're just spaces between strong patterns. All right,
Strong
so
patterns sound like generality to me. I mean, that's kind of the route to generality, it seems like, is with strong patterns. I mean,
right. The only reason you know if that pattern is general is by the results of previous level of cross comparison, because that's what cross comparison does. It finds what is in common among the elements, and common is just another word for general.
right.
All right, so basically when you have this cluster, it's already a generalized representation of the inputs. It's actually a multi-level representation. Okay, it has the summed parameters of the inputs. Again, those parameters are derived from cross comparison, but then they are summed. As opposed to statistical processing, they are not summed within random samples. They are only summed within those patterns that are defined by match between the elements. So you only sum if you have a match. All right. And so those sum parameters are compressed because you have one sum parameter per whole bunch of parameters in the input, individual input parameters. So in this sense, the compressed and generalized is the same thing, because you can only compress what is in common among inputs. And again, it's synonymous. Okay, common and general is just two different words for the same thing.
That's interesting. Any other questions for Boris? Stefan, did you?
Yes, the example that's currently being documented, it uses one dimension. So it's one continuous array of elements. If you would be processing an image with 2 dimensions, so an XI grid, how do you select priority of the dimensions? How do you know which is the ideal dimension to combine to cluster first or second?
Well, initially you don't. You can only do it after processing, and I call it dimensionality reduction. That is, initially, if you have this cross comparison inside kernels, it's done in all dimensions at once. They are assumed to be equal, of equal importance. Okay, and again, clustering through flat fill is also, it doesn't really matter in which direction it goes first because the result is the same. Now, once you have a blob, and the blob here could be an area of high gradient or area of above average gradient or area below average gradient. And if it is above average gradient, then it will represent essentially edges of you can look at it as let's say flat areas where things don't change much, and the edge areas where things do change more than average. And those edge areas are generally they look like curves. Okay, they look like again they look like edges of those flat areas. Okay, and basically what happens here is this is in my 2D algorithm. The second step, I call it comp slice. Okay, what happens is if you have this high aspect blob, which is an H, high aspect means that in the first, it is likely to be high gradient blob. And second, that blob is likely to have a big difference between, let's say, vertical and horizontal dimension, no matter how you call it, because again, it's an edge which looks like a thin, long blob. Okay, so you have a primary dimension, you have secondary dimension, the primary being the long one, and the secondary is across it. But you don't actually know the direction of that dimension, of the long dimension. But it's like you do a linear regression. Actually, what's the right term for regression where it's regression to a curve as opposed to a straight line?
Logistic regression?
I don't think it's logistic. Logistic is more like it's still linear, but in different proportion. There is a, I think it's called curve fitting or something. All right, that doesn't matter. So basically, you have those long thin blobs that can be reduced in dimensionality from a blob to you have to basically trace them and define the primary dimension, a long one, and then what you do, the way to do it, okay, you slice it by the horizontal dimension, however it is defined, and then you compare the slices vertically. Okay, once you compare the slices, you can see, you can vectorize the representation. A vectorize meaning you have a raster representation, which is just a bunch of pixels, and you can convert it into a vector, which is.
So what you're describing is I think a transform.
Transform, it could be anything. I hate those those terms that can mean anything. Okay, it has to be more specific than that.
Exactly, it can mean anything, but your steps are anything. They're a string of
well, they're not anything. They're specific code. If you look at GitHub, the code is very, very specific. Okay, and there is only one way it could work at every step.
each step is different.
Well, the steps are different, but the sequence is predefined. I mean, not the sequence, but let's say the branching in the sequence is predefined.
Yeah, so you're seeing a smile or a face or whatever. You've got some kind of dimensionality that or pattern that you found within the data.
Well, yes, basically the patterns, they have to be structured. They have to have positional information. The problem with neural networks that you can kind of get positional information, but it would be separate from the value proposition. It's like in the brain, you have separate pathways for what and where. Okay, those positional information is represented in one place, and the actual value representation is somewhere else.
I'm not using a word transform in the neural network sense. I'm using it in the mathematical sense, like a Fourier.
See, again, in mathematical sense, trace anything is a transform.
Exactly.
And so it's really a meaningless term.
I mean, at the basic units of your system, it's a blank mind. You have to put input into it. It is meaningless at the beginning.
Well, no, yeah, the input is, yes, meaningless in a sense that doesn't represent anything, but it is a very specific process of processing that anything.
Mhm.
And transform is also a process, but it's not specific. It could be that process, that word can mean any kind of process.
Exactly.
And in my case, the process being the code, it's not anything. It is a unique sequence of operations.
Your diagram has 4 operations. There are more.
Diagram is pretty vague. I mean, yes, it's all operations. Obviously, if you want to see how it works specifically, you would probably first go through one-dimensional algorithm, which is that 1D log file on GitHub. It basically shows what exactly happens, and it's always easier to. Sorry.
I'm looking at the specific table that was showed earlier. And the first one is unary.
Yes, the table doesn't have dimensionality built in. It could be any dimension, any dimensionality.
It goes from less complex to more complex.
Yes, but it's not, that complexity is not in Cartesian dimensionality. That's a separate kind. You basically on each with each dimensionality being even if it's one dimensional, it can go through all those steps. So those are separate things. Okay, you can have 1D input, 2D input, and 3D input, and each of them would have to go through those 4 initial levels of processing.
Have we got any other questions? Oh, go ahead, Boris.
Yeah, so basically, again, those are predefined parameters. You have modality for the value of input, and you have a Cartesian dimensionality for the position of the inputs. And that is a kind of shortcut for the algorithm discovering the difference between modalities. You can have, like, let's say, input of mixed modalities, where the algorithm figures out, basically separates between them, which is a long, complex process, and it's pretty hard to design. Well, the design would be the same, but you won't get results anytime soon. It will only separate them after some time. So it's pretty hard to design code for it, I mean, if you want to run it. And the same thing with dimensionality. You can have the same basic principles implemented for strictly one-dimensional input, time only. Or you can design it in 2 dimensions or 3 dimensions for a 2-dimensional or 3-dimensional or 4-dimensional input. Okay, and again, theoretically, the algorithm itself would be able to discover higher dimensions even if it is given a single dimensional input that actually represents 4-dimensional universe. But if you want to run the code and actually see something happening in real time, you better use some shortcuts. That is, you first, it doesn't make sense to mix up different modalities if you already know that they are separate, and it doesn't make sense to mix up the different dimensions if you already have this 2-dimensional or 3-dimensional matrix on the input. And so I'm using this structured input because it just it saves a whole lot of time, a whole lot of learning. Okay, learning process. If you want the code to actually work in real time, you better build in those shortcuts. All right, but conceptually, you don't need multiple modalities and you don't need multiple dimensions because there is really no limit to modalities you can include. I mean, initially you may have this audio and video, and actually video is 3 submodalities on its own because it's red, green, blue. And that's really arbitrary because that's simply the way human vision works. It doesn't have to be red, green, blue. It could be anything. It could be ultraviolet or, radio frequency, whatever. Okay. And it so happened that our universe is 4-dimensional, but general intelligence shouldn't be tied to that. General intelligence should be able to discover whatever dimensionality that universe actually is. And so if you just want to design a theoretically consistent algorithm, you start with a single modality, which is just grayscale video. And you start with a single dimension, which is just basically a horizontal scan line across an image. And even then, once you're done with it, you already have all the basic principles implemented, and then it's a lot easier to translate the process into, let's say, 2-dimensional input and 3-dimensional input, which is what I'm doing. That's why I have this sequence in code. You start with 1 dimension, then you extend it to process 2 dimensions and so on.
Well, we've got about 10 minutes left, it looks like. Any other comments, questions?
I was just wondering if Boris could describe the big picture. You're targeting intelligence. You've got a box in front of you, a gray box with a processor in it, some signals representing environmental feeds of different modalities. What's it doing? I mean, what's the big picture for a product?
There is no product. Not that I care about.
What problem?
The big picture is open-ended. It's an exploration. It never stops.
Okay.
Okay, it's like science. Okay, what's the big picture? What's the end product for science? There isn't any. It just goes on to explore the universe.
Okay, so this is a journey for yourself.
It's not a journey for myself. Myself is just a means to an end.
Okay.
Okay, it's a journey for exploration. Okay, it's an end, not a means.
Yeah, well, we all have that, I suppose, one way or another. In my particular case, I'm headed towards cognitive robotics. So I'm interested in making machines that behave intelligently, and that's the goal. So I suppose that's my journey.
Well, the
in 10
thing
years'
about
time?
robotics is you have to say have an action, meaningless action, constructive action is always a feedback, and you can't have feedback without feedforward. So whatever your end goal is, you have to make sense of the environment first. Okay, you have to have a perception before you have action.
Yeah. Well, the two in nature, they come together. And itself.
Yes, it depends what kind of nature you're talking about. It depends what you mean by together. They don't actually come together. Perception is always first.
No, I'm talking about the
B,
way evolution actually created creatures that operate in an environment.
well,
I mean,
yes, those creatures are not what I would call intelligent initially. They're
all
not
right,
intelligent, and they're not
I can
intelligent.
see how a bee is intelligent to some level, in that it can survive in an environment with a great deal of novelty in it, and engage in its own survival in an innate fashion that comes built into the biology of it.
Biology it has multiple steps of evolution in it, and you can basically the way I see it is intelligence. How should I explain it? Biology has one fitness value, which is reproduction. Okay, essentially, when it starts, it's all about reproductive fitness. Okay, it's not about survival; it's about reproduction. Okay, so it has this value of maximizing reproductive fixed fitness, and cognitive process is a higher order process, higher order compared to evolution. It doesn't maximize reproduction on its own; it maximizes prediction. And you can think about it. You may say that, oh, okay, that's just instrumental to reproduction. Well, the problem is that instrumental values eventually take over. It doesn't matter what the original value was, okay? Yeah, it's like with instrumental conditioning. You may start with some values and end up with completely different values.
Yeah.
There is the thing called value drift. So just because it started with reproduction, and then it went off to something more complex like 4Fs, that doesn't mean it has to end up with it.
No, I'm sorry, I'm not following any of it. Clearly, I'd like to know what the end game is.
There is no end game. It's progress. It doesn't end.
So Boris, I got, it seems like you could, if you wanted to, create some kind of application. You might not want to, I realize, but
no, the application wouldn't be anything effective until I have more or less complex system, because essentially it's not supposed to do anything interesting until it goes through a whole bunch of recursion. The algorithm is supposed to be recursive. And so, yes, I could do something that does something, but it won't be competitive with anything out there. It won't be interesting until I have, it's like I need an algorithm that is the kernel of recursion. And only when the kernel is complete, I can actually do the recursion, which would be an effective process. So it doesn't make any sense for me to do a recursion on the algorithm that is maybe 10% complete, because the results are going to be totally different from the results you get from 99% complete algorithm. In recursion, at each step, whatever variations you have in the algorithm, they grow exponentially. And so running an algorithm which is not nearly complete simply wouldn't give you any idea of what it is capable once it is complete.
What do you expect, though, once it is more complete? Do you expect it to be better than deep learning? If so, how?
Well, I basically already tried to explain it. Yes, it's supposed to be better because it's not. It doesn't have to be. It doesn't need training. It doesn't have to go through 50,000 cycles to learn a single picture. It is the process is not destructive. Okay, the data is not totally degraded at each level, and because it's not degraded, it has the information that you need to process on higher levels without going back and forth gazillion times.
It seems like one of the benefits, if I understood this correctly, was that the kind of the, I don't want to, probably you don't want to hear the word concepts, but concepts can kind of come together. You're not throwing things out, you're kind of
so basically concept is not a well-defined term.
yeah,
To me,
kind of
concept
expected
is
that
just
reaction.
another name for a pattern.
So basically the patterns would come together. You wouldn't, I mean, the way deep learning often works is, you know, it's fine for some domain, but the problem is transferring it to a new domain. But it seems like what you've envisioned anyway is kind of a coalescing of patterns where you don't have to throw out some patterns because they don't fit the domain.
Yes, again, the
It seems
process
like
is
that's one of your
pipeline.
objectives.
Yes, again, there is no catastrophic forgetting, what they call it.
Yeah.
When you switch from one domain to another, you don't have a connection. That's because the system in deep learning can only work as a whole. That is, you have to go back and forth across all levels to train it. Now, in my case, the process is pipelined. Each level can work separately. Essentially, it can work through message passing. Okay, is you have the inputs which are displaced by new inputs. They are not destroyed, they go to higher level, and they're still represented there. And you can think about it as like inputs in different domains, only inputs in the same domain between different types of let's say different types of animal, whatever you train it for, that compression and that pipelining allows for, again, this is the difference between distributed representation where everything is processed all at once, essentially. Okay, you have to go through the whole network to train it. And this localized representation where each level and each node in the level can work to a large extent independently. And it can form local representations of the inputs which originally came from different area or different level. And that's why the representation on these different areas or different levels can change.
Yeah.
It can change without destroying the data that was in them before. That data is already on higher level.
I think I understand your main kind of your main objective there, and yeah, they can combine, right?
Yeah, the whole process is basically a process of composing more and more general patterns out of lower level patterns. So you can call it combination. Okay, I call it composition. It's really the same thing.
I'm wondering why you mostly restrict yourself to 4 dimensions. As you said, your entity can be in infinite dimensions if you want. Why are there only 4 rows on your table, and why doesn't it go to infinite dimensions? Or other specific dimensions?
Because the 4 rows have nothing to do with dimensions, as I would call it. Okay, it's 4 steps of processing regardless of dimensionality.
Okay.
Okay, and I don't restrict them. I did say that what I'm designing is a recursive process of generating new levels. Okay, there are 4 levels of processing. from digitization to centroid-based clustering. And there is a regularity in transition between the levels. You have incremental composition, incremental quantization of inputs, incremental power of comparison, and so on. And because those things are incremental, I can form higher levels by incrementing those things. This process of forming new levels is supposed to be recursive.
So that doesn't have anything to do with the 4 dimensions.
No, it doesn't. The 4 dimensions is a completely different thing, and it has nothing to do with table either. 4 dimensions is just what our universe happened to be.
Well, some people would beg to differ. Some physicists think there are, various dimensionalities.
Well, yes, you could eventually discover high dimensional properties, but the fact is that in our immediate environment, 4 dimensions is a plenty.
Well, why don't we wrap things up? We're pretty much out of time. Hey, Boris, thanks a lot.
Yeah.
Thanks, Greg. Thanks, Mike. Appreciate you guys having me here. Sorry I didn't go through that video thing. Again, I mean, if you have any kind of questions, I mean, it's either on Meetup or on GitHub or on comments on all, whatever. I mean, we can continue it. Basically, we're not restricted to a single event. If you care, of course. So, all right. I guess we're out of time, right?
Well, well, pretty much. We set it at an hour and a half. But I'll post the video
And
pretty soon.
contact points as well.
Yeah.
Okay.
You could put your Boris. Maybe if you put your email in the chat. Oh, I don't think you have access to chat, but I think we can get in touch with you through your web page, which is posted on the meetup.
Yes, I'll post the email on the comment.
Oh, you can. Okay, you can do that. Okay.
Yes, I'll do that.
So
it could be email, but again, there's you can start a conversation on GitHub. That's the easiest way.
Okay.
GitHub, my GitHub page has conversation tab on top. Okay, and you can start a conversation there.
Okay.
I mean, if you want it public, of course. If not, I mean, again, I'll put email on in the comment, but generally there is no limit of ways that you can put a comment in the introduction, or you can contact me through GitHub. It has my email, or you can just Google me and you will find it. It's not terribly secret. I mean, it's really boris.kz@gmail.com.
Gotcha. I think our next meetup might be an in-person one. I don't know, Lance. Is that something we're?
Yeah, if you guys want to, we can do a kind of a more of a social one next time.
It would be. Well, it might turn into kind of an annual thing. We had one last summer.
Yeah, it was fun.
Yeah. And again, if anybody has ideas for another event, let us know. And any last comments? Manny from India, did you want to say anything? I was talking to you a little bit. I don't know if you're still there. Manny? I guess not. You checked out. Okay, so that pretty much wraps it up. Thanks a lot. This was interesting. I like hearing these kind of alternate approaches personally. And see everybody next time. Colin?
Cheers.
Cheers. Okay. Good night or
Take care,
good
guys.
morning or whatever it is.